look at why it cannot cross, why integral curves cannot cross each other. Okay, so as I was saying, integral curves can't cross each other, can't cross each other. Okay, that's the first thing which you need to understand, why it cannot cross each other. Let's say that one integral curve, so there are two curves which crosses each other, right? Something like this and something like this. The point where it crosses each other, just look at the tangent line at that point. There is a tangent line which looks like this, and there will be another tangent line which looks like this, right? So there is a slope m1 and there is a slope m2. Clear? There is a slope m1 and m2. So when it touches each other, so let's say let two integral curves crosses each other. Okay, cross each other. Then what happens? Then at the point of intersection, you have one has two slopes, two slopes. Okay. Now, is it possible to have two slopes? It won't, because you see at this point there is one particular slope. So this point in R2, if you understand, if you remember, every point, okay, every point has exactly one slope assigned to it. Okay, so but here if they cross each other, then at this point there are two different slopes. Okay, that cannot happen, and that is why integral curves cannot touch. And it is also evident analytically. See, if at some point there are two slopes, then y1 prime equals to f of xy1 and y2 prime equals to f of x y2. If there are two different slopes, then y1 prime and y2 prime are not same, and that is why f at x y1 and f of x y2 are not same. Okay, that cannot happen, because for any common point you will so basically you are saying that at one point x naught. See, essentially at this point what is happening, y at the point x naught is y2 at the point x naught, right? Okay, so that will imply f of x y1 at the point x naught. Okay, if this happens, okay, f of x y2 at the point x naught, that should happen, right? So that will give you y1 prime equals to y2 prime. Okay, so that will imply that y1 prime equals to y2 prime, right? Now so basically at every point there is only one slope assigned. If there are two slopes, then you understand that the function will be a multivalued function. That cannot happen. Okay, so what we can say is integral curves cannot cross each other. Okay, now let's understand that if the integral curves, what is the case 2? Case 2. Okay, so what happened to our case? Our case, you see, this is this c equals to 1. Let's say this is c equals to 1 and c equals to 2. um, c equals to 2, c equals to 0, and again c equals to minus 1, c equals to minus 1. So as we are seeing that our integral curves are coming like this, right? So let me put it in blue, the integral curves. So they are taking this particular, one sec, they are taking this particular route. See, sorry, I should, they are taking this particular route. See, they are coming like this, and I mean coming from infinity and going towards this line c equals to 1, huh? And moreover this is also doing something like this, huh? It is going like this, and here also same thing is happening, here also same thing is happening, something like this. Okay, and of course this is also an integral curve, if you remember, this is also an integral curve, so this is going like this, see. Okay, now the question is this, the second question. So first of all, it can't touch each other. So these and these cannot cross each other. This and this cannot cross each other. The second case is, can it do this thing? Okay, at some point, does this thing happen? Okay, so integral curves cannot touch each other in this case. In this case, okay, why it can't touch each other in this case? See, the point is, where let's say this is another integral curve and that's another integral curve, which, so this is y1 and this is y2, okay, both are solutions, they are integral curves to this equation, and they touch each other at some point. Let's say this point is x naught and y naught. Okay, so there is something called a Picard's theorem. I think you guys have heard about it, Picard's theorem. Okay, so what does the theorem say? The theorem says that if is continuous at some point, continuous at x naught y naught. I am not writing the proper theorem. Huh? We will do it in the next class. So if f is continuous at x naught y naught, and I am saying that if del f del y, this is less than m in some neighborhood n delta of x naught y naught. Okay, delta positive. Yeah, then f y prime equals to f of xy, okay, admits a unique solution, admits an unique solution in a neighborhood of x naught y naught. Clear? In a neighborhood of x naught y naught. What it means is, see, it means that if you change, I mean, it says that at this point, at every point in, okay, so now for our equation y prime equals to x minus y, you can see that f of, which is equals to f of xy, let's say. Hmm? You can see that f of xy, f is continuous at every point, and del f del y is minus 1, which is always bounded by m in any neighborhood of x naught y naught. Okay, so essentially you can say that this equation admits a unique solution in a neighborhood of, sorry, I should write it in a neighborhood of x naught y naught, because the problem y depends on x naught, in a neighborhood of x naught. Okay, okay. So essentially, what I'm trying to say is this. See, Picard theorem holds here. So at every point x naught, okay, you have a unique solution. At least in a neighborhood of x naught, you have a unique solution which satisfies the equation. But if it touches each other, then what happens is, in that neighborhood of x naught, okay, you will have, so if you take a sufficiently small neighborhood also, you will have two different curves which satisfy this equation. Okay, which is not possible. So mm, uniqueness uniqueness forbids integral curves to touch each other. Okay, hence they can't. Okay, so essentially what I'm trying to say is, this thing won't happen, this thing won't happen. Okay, so these, all of these will, up to infinity, this will become asymptotic. Okay, this will become asymptotic to this line. You see, it will become asymptotic, all of this, they can't touch each other, they can't cross each other, so they will become asymptote to this line. Okay, it will go on like this, and you understand that it will just as it goes towards infinity, it will just go asymptotically towards this line, but it will never going to cross or touch that particular line, because in this case this is an integral curve. Okay, right. So, and you can see what is the solution of this thing. See, dy by dx, if you equals to x minus y, that was our problem, right? And yx equals to, as you have seen that 1 is a solution. Yes, yx equals to, that is what we found, yx equals to 1 is a solution. What did we found? We found that, yeah, you see, x equals to y plus 1, c equals to 1, that is one solution, right? Okay, see, you can take a general solution. So what you do is this, so this, please you guys check, huh? Find a general solution. So find a general solution, find a general solution, okay, and check that the general solutions, okay, converges asymptotically to x equals to y plus 1, that c equals to 0, c equals to 1, I think, huh? Or c equals to 0, c equals to 1. Okay, c equals to, corresponding to the slope c equals to 1, that I should write x equals to y plus 1. It converges to that. Please check this part, and this is how you trace a integral curve.